we go. So I decided I was going to be an architect when I was 10 years old. My Uncle Larry was an architect. He studied with Frank Lloyd Wright. He drew beautifully, and he drove a Corvette, and I thought that was really cool, and somehow I could emulate those things. And really, since my parents weren't going to give me a Corvette, they gave me some drafting instruments and a drafting table, and I started playing at being an architect when I was 10. And drawing really was what was interesting to me. I loved to draw buildings, and I drew a lot. And the question we're going to talk about today is, what is the meaning of drawing in the making of buildings, and why is it, and what I've got here on the screen here is my collection of antique drafting instruments, and in the middle of that collection are the instruments that my parents gave me when I was 10 years old that have now become largely obsolete, and the means by which people go about making buildings has really changed in a pretty profound way. Now, drawing has always been a mechanism that architects and builders have used to talk to each other to figure out how to make buildings. And this drawing, which is one of my very favorites, I first saw in the British Art Center in a show that was about the mathematics of construction a couple of years ago. This is a drawing by an architect named Robert Smithson. And what Smithson is trying to explain in this drawing is how to do something very complicated. He's trying to draw a round rose window in a curving wall, so it's a double curved window. And in addition to it just being a very beautiful artifact, this drawing also has in it all of the logic of both the end result and the making of the artifact itself. The actual masons who made this window could use this drawing and go out to the building that they were working on and finish that rose window with some very, very simple geometry and some very simple instructions. And the question that I've been thinking about during my career is, what is it that makes this sort of thing happen? And how is it that buildings are made today and were made so differently really in the past? I was lucky to be able to come here to Yale to study architecture, and then I went out to California to start my career. And this is one of the very first buildings that I worked on. This is the Oakland Federal Building in downtown Oakland. And at this time, which was in the mid-1980s, we began to get interested in the idea of computers. And for the students in the audience, that's what a personal computer looked like in 1984. That's called an IBM XT. And I was interested in what that device might mean for how we would go about making buildings, but there was no such thing as computer-aided drafting at that point. So we bought that machine, and we had to hide it in a closet because it was so terrifying to the older architects in the office that I spent 2 years working on things like budgets and schedules on that machine hidden in a closet because computers were so terrifying as a phenomenon in the making of buildings. A little bit later in my career, I was able to come back here to New Haven, and I worked for Cesar Pelli, who's an architect up the street. And at that point, computers were starting to emerge as instruments that we were beginning to use to make buildings. On the left-hand side here, you can see a couple of drawings that we used. We used computer-aided drafting. You can see there's a much younger, much hairier version of me in the photograph on the left there with a giant model that we built that was 30 feet long because we wanted our clients, this is Washington National Airport in Washington, D.C., we wanted our clients to really understand how big that space was going to be. And there wasn't any other way to do it except building physical models. And today, in the age of games and high-resolution images and computer-generated renderings, we didn't have any of that stuff in the early 1990s. So what we did was we took these drawings on the left, and we built these physical models here that you see on the right. And then we would photograph those physical models, and we would color them with colored pencils. We'd color the photographs with colored pencils so we could get some idea of what was going on inside those spaces. In fact, we used a little trick. We would stick a mirror in the back of the model, so we only had to build half as much model, right? And then the thing would double, and then we'd print it out big, and we'd color it. And it was thousands of hours to produce these kinds of images, and the computers were really just starting to emerge as part of the overall process. Now, a little bit later in my career, I worked on this project. This is the Miami Performing Arts Center in downtown Miami, extremely challenging project. 2 big performance spaces that cross Biscayne Boulevard. The project took 13 years to complete. There were about 40 firms working on it, thousands and thousands and thousands of drawings. and many architects and engineers traumatized in the process of trying to get this building done. And in a way, at this stage, at least in my career, I was starting to get interested in the processes. What was it about the way we made buildings that made it so challenging and so difficult? And so ultimately, this was the last building project that I worked on when I was working for Mr. Pelli. This was the corporate headquarters for Goldman Sachs in Jersey City. You may recognize this building. It was ultimately built 10 stories shorter. It was shortened after 9/11. And this is a computerized rendering. This is a computer-generated image of what we wanted this building to actually look like. So by the late 1990s, we were able to really understand pretty deeply at least the three-dimensional qualities of buildings, and we could generate reasonably high-resolution images that showed us what these things were going to look like. And as we'll talk about in a minute, my experience with this tall building turned out to be an interesting touch point in this future. So as I was working on this project, I got a call from a headhunter. And this headhunter was looking to hire an architect, what they call a domain expert in my current job in the software world, an architect to come in and help think about the strategy that our company that I now work for uses. I work for a company now that makes a lot of digital technology for architects and engineers. And I started by talking to our software development teams and asking them the following question. This is a little sketch that I did called Phil's Garage. My wife Nancy and I needed a little garage behind our house in Westville. And the question I wanted to know was, how is it that I can do such a simple little drawing like this? This is 8.5 by 11 inches, pencil, ruler, football game, beer, very simple, straightforward drawing that would describe to any competent carpenter or contractor how to build this entire little garage building. The structure is in that drawing, the details of the windows, the three-dimensional characteristics. And for a very simple building type, drawings seem to make a lot of sense. In fact, as architects and builders, we've spent thousands of years perfecting this secret code that we use to describe how buildings are actually built. But the question really now becomes, what are the results of the use of that kind of secret code? So this is my museum of fun things that happen in buildings. Some challenging problems here. Gentlemen, you might find some difficulty in using the men's room on the lower left. We have the stair to nowhere here. The ATM that's a little tough to get to, doesn't meet the handicap requirements. And then, why let the street lighting get in the way of your balconies? You just build the building around it. And any of you who've been involved in construction have seen these kinds of challenges before. And they're fun, and these images are funny, but construction is a very, very expensive enterprise. It's one of the largest consumers of gross domestic product in the world, and generally speaking, the studies that have been done in Great Britain and the United States suggest that out of every dollar spent on construction, about 35% of that dollar, 35 cents, is wasted on stuff like this, and the kinds of mistakes and errors and problems. And for buildings in the United States, that can be about 140 billion US dollars a year, or about roughly 8 times the amount of money that the architects got paid to design the buildings got wasted during the construction process of the buildings. And at the same time, our buildings generate huge amounts of carbon. Your SUV generates about 6% of the carbon that gets dumped into the atmosphere. The nation's buildings are responsible for 40% of the carbon. So there's some serious challenges here that really need to be looked at. Now, at the same time we were working on the airport in Mr. Pelli's office, we were also working on this building, which is the Petronas Tower in Malaysia, and we were using early versions of computerized drafting tools. And one of my favorite drawings that we used to build the top, you can see this is the drawing of the top of this tower. This was the drawing that was made by the guys who built the top of the tower. And what they did was they used a piece of software, and they made this drawing by looking at a printout of another drawing made by an architect using exactly the same software. So they would plot the drawing out, and they would copy it line by line. And then what we would do in order to resolve our questions is we would FedEx this drawing back and forth across the world using a very sophisticated tool called a red magic marker. And we would mark on these drawings lots and lots of complaints about what was working and what was not working about those particular drawings. And really the problem looks something like this. Here's the dilemma. This is my little sketch of, a simplified sketch of how a building actually unfolds. Architects think hard about how it's designed, then cost estimators figure out how much it's going to cost, then somebody builds it, somebody goes out and operates it, and here is what we know about the project, more or less. So the architects start working and they start building up lots and lots of expertise, and as soon as they're ready to hand their expertise over to the next phase of the process, even though they've got lots of insight, they plot it out on pieces of paper and then challenge the cost estimators to actually figure out how much it's going to cost. The cost estimators go through the same process. They do lots and lots of measuring, they collect lots of information, they're thinking deeply about the building, and then they hand all their information on pieces of paper to the contractor. Now the contractor goes out into the field, the guy who's actually, the folks who are actually building the building, and they're accumulating huge amounts of knowledge because they're actually there in the field watching the building get built. They know where all the mistakes are. They know where all the wires are. They know where all the pipes are. And at this particular moment, the knowledge of the project is at its absolute peak. And 5 minutes after the building is built, the contractor rolls up all the drawings and hands them to the owner. And then we get another one of these big drops. And then the owner spends 20 years trying to figure out how to operate the building. And we began to wonder, why couldn't we have a smoother curve? Why couldn't we actually have a more integrated process? And so what we were thinking about was, how is it that this image on the left, this is a Boeing 777, which was completely designed with no paper. All the information about that plane fits on 7 DVDs. Why is it that that's the process that gets used to build airplanes? And this is what an architect's office looks like these days, right? Buried under all this paper is his drafting table. Right, and this is an older picture, but his monitor's not big enough because he had to make it bigger with Post-it notes, right? He's using paper to actually expand his degree of insight. And we were using computers to kind of make drawings like this, but our colleagues in the manufacturing business were using computers to do things like this. This is a digitally simulated bubble wrap machine. This machine makes bubble wrap. And what you're looking at in this piece of software is a digital simulation of that machine. The designers who put this together can run this complete digital simulation and understand how this machine works, how much electricity it uses, how much metal is in it, how long it's going to run, where you're going to get your fingers caught in it. And we begin to ask ourselves, why is it we couldn't do that with buildings? Why couldn't we make buildings? Why couldn't we make images or models of three-dimensional buildings that work in a similar way? So our company at that time was the world's largest provider of CAD software, drawing software, and we decided we were going to try something different. So we introduced this concept called building information modeling. Building information modeling was this idea that instead of making drawings, you would make a digital model, a behaviorally correct digital model of a project, and by virtue of having that model, you could change a whole bunch of stuff about the way people work together and the way they actually made buildings. And we began working on this problem. We bought a small company. We started talking about the idea that maybe CAD wasn't the future. And then one afternoon, there was one of these moments of impact. I happened to find myself sitting on an airplane next to the senior architect who was responsible for the construction of this very important project, which is Freedom Tower in New York. And we got to talking about some of the challenges that he was facing in making this very, very important project really start to work. And the discussion was actually quite interesting because his problem was not, how do I design the world's tallest building? That's a pretty simple, straightforward problem above the ground. But below ground is this enormously complex thing. It's got trains and stores and columns and pipes, and it all had to be this incredibly worked out three-dimensional thing that the main tower that you can see here in the background would actually ultimately sit on. And so they decided they were going to do an experiment with building information modeling from the bottom, and then the design team got so excited about the process that they just sort of ran up and did the rest of the building. And we were nervous about this. We were nervous about it failing, but these guys continued to do their work and model this thing out. And then in July of 2006, this other moment happened where this article was published in the Wall Street Journal. This was on the second front of the Wall Street Journal talking about the use of our new technology to design this very prominent project. And that was really the moment that began the change in our overall industry. Every partner of every architecture firm in the United States came out of their office and threw this paper down on their staff's desk and said, why are we not doing this? And it's very interesting that those two moments sort of aligned to make this sort of happen. So in 2008, we decided that our company, needed to try this science experiment on our corporate headquarters, which we built up in Waltham. And what we really wanted to do was test the technology to see if we could create a highly collaborative, highly sustainable, three-dimensional approach that would allow you to do these kinds of buildings. And one of these things these digital simulations are really good at is measuring stuff, right? Simulating how much daylighting there is, simulating how much water is being used, simulating how much energy is being consumed. But at the same time, it also creates an environment in which everyone can work together. Everybody can kind of see what's going on. People aren't guessing about drawings anymore. They're not shipping drawings back and forth across the world. And in this project, it was really the sociology of this project that was most interesting, not the design. The contractor would publish these three-dimensional images of the building and post them in the elevator every day and say, gentlemen and ladies, this is what we're working on today. He would create these 3D renderings. That looks like a plasma TV, right? But it's actually just a plot on a piece of greater form that says, today you're going to build something that looks like this. No drawings, just a 3D image. And this is maybe the most interesting image in the entire presentation. This is non-union and union workers in the same ceiling in a Boston construction project. Usually this guy is hanging the ceiling and this guy's picketing the job site. So the fact that these guys could see the project with such clarity really meant that they were willing to change things and change their process in an interesting way. And you'd walk the job and you'd see all kinds of weird stuff, right? You'd be walking through the job and you'd see this pipe jump up in the air. And then you'd walk by that pipe 2 days later and a piece of sheet metal, a duct, would go right past it. Normally, that pipe goes straight across, and those guys who put that duct in charge you a ton of money because it doesn't fit. So even these kinds of simple ideas resulted in a different dynamic, in a different way of working. These are my baby pictures of our office. We were able to take some of those inefficiencies, some of that 35%, and spend some extra money to make this office a little bit nicer, and it really came out really well. And even here at Yale, here are some of James Gamble Rogers' drawings on the left of Harkness Tower, and this is a Robert A.M. Stern architects who are doing the new colleges. That's an image directly extracted from their building information model. That was a challenging project that the dean asked me to be involved in, a Gothic building using 21st century technology, really pretty challenging. And so now we're 10 years into this proposition of trying to shift people over. Most of the architects and engineers in the United States have made the change. We've disrupted this 2,000-year-old tradition, and things are starting to happen across the world. This is one of my favorite photographs of the BIM breakfast happening in Dubai last year. People sitting around talking about this stuff, trying to figure out how it's going to happen. And really what the proposition here is about is changing the nature of the work process. It's not just getting away from the strictures that my old drafting instruments put on me, but really changing the way designers work. And this particular designer is trying to create a stadium enclosure where she's trying to make sure the sight lines are all working to the soccer pitch and use the minimum amount of steel possible and still solve the structural problem. And what she's able to do by using this digital model is look at the relationship of all three of those things at one time. So we've not only changed the sort of nature of how people work together, but we've changed the process as well. And so in the future, we really do believe that things are going to change. I got this, this is a photograph that I got from some of my friends who are contractors. This is their vision of the future working in the construction trailer, right, with the digital models and the virtual iPads and the digital trusses. But I said to them, this is a fantasy not so much because it shows a digital model of construction, but if that's a job trailer and you guys are in it at night, this is a fiction because contractors never work. They never ever work at night. But in case you think these visions are wholly original, in some of my research for this talk, I came across this postcard in the library. It's a French postcard from the year 1899, talking about how the architect is going to work in the year 2000. And in this particular view of the world, this architect is sitting in his robotically controlled a booth here using a robot to build the building without any contractors whatsoever. I don't think that's actually where we're ultimately going, but we do think we've made a little bit of progress in changing the nature of the process and the tools that people use to accomplish it. Thank you.